Hey guys, so this YouTube video is going over the method of sections problem. This problem is the problem that Professor Rob started to go over in his lecture, but you can use the method that we use in this problem to solve the last problem that's on homework 5. So the first thing is you're given about this much of your section right here. For the method of sections, you're shown that much of your truss system. What I have dashed here is the rest of the truss, just so you know what it would look like. But when you do the method of section, you're focusing on this section that's drawn out in blue here. And then what you're solving for are these three unknowns that I've outlined in red, and I've shown the direction that we're assuming them all to be in right now, which is that they're all in tension right here, because remember that if tension, they'd be pulling away from all sides. But this is what you would be shown in a drawing. You wouldn't be like given, this wouldn't be a hard drawn, this would be like dashed in the background like these are. So a couple things to remember. For the method of sections, you're looking at a section or part of the truss to determine the load that each element holds. So you're determining the load of these three elements and then whether they're in tension or compression by looking at this section. The biggest difference between method of sections and the other method is that in this one we're going to look at the sum of the moment. So we're taking the sum of the moment about A, B, and E, which are these 3 points right here. The other thing to remember is that you're doing the sum of the moment on the elements acting about or around that point and not actually on the point. So I'll explain this as we start the process. So the first thing you're going to do, step 1, is the sum of the moment about point E. So if we're doing the sum of the moment about E, then it's things that are not actually touching or acting onto E. So like BE is acting onto E, so we're not looking at that. We're looking at this R1 right here, this P1 up here, and this BC right here, because those are acting about E but not on to point E. So R1, it's the sum of the moment is force times distance, and in this case, because we have a truss, it's the perpendicular distance that that member is from your point. So R1 is acting over here, and its distance from E is 12 plus 12. Those are given to you, so it's R1 times 24 feet. And then P1, we do the same thing, and it's 12 feet because it's only 12 feet away. Now you'll notice that R1 right here is a negative and P1 is positive. And we're doing the same thing we've always done, where it's counterclockwise is positive and clockwise is negative. So if I were to put my finger on point E, P1 is pointing down, causing this to rotate this way, which is counterclockwise, positive, and A1's going up, curving this way, which is clockwise and negative. Now, when we get to BC, that's where it gets a little interesting. So you've never seen a point, like had to know whether this was clockwise or counterclockwise. But if I put a point here, or a beam, and you have something going this way, it's going to cause the beam to do this, or curve like this. So it's also clockwise and negative. Now the perpendicular distance that this BC member is from point E is this length right here. Now you're given this length, these lengths, and you're given this length. So this distance right here is what we need to know. And you can see there's a triangle right here. So what I've done is made a triangle to show you that you can just use Pythagorean theorem. So you're missing this side right here, this height between E and B. And then when you do, when you solve Pythagorean theorem, you find out that leg B is also just 12 feet. So in the same sense, you could be given this distance and this distance, but not know what this leg is, and that comes into play later. But you can just solve it with Pythagorean theorem. So now you have set up your sum of the moment about E equation, and you're just going to plug in your numbers for R1 and P1 to solve for BC. It's just algebra, just like we've been doing before. Now when we solve for BC, we see that it becomes a negative number. And as we know from before, that means that our assumption of the direction is incorrect. So in this drawing, BC is assumed to be in tension, but since it's a negative, we know that it's actually acting in compression. And it's important that you write this out so we understand that you know whether it's in tension or compression. So step 2 now is to do the sum of the moment about B. So if we go back up to here and we look at point B, we are looking at the things acting about B, so around it. So R1 is over here. We've got AE acting this way as well. Those are our only 2 things acting about point B. I'll zoom out a little bit. So we have R1 that's still going clockwise, so it's negative, and it's 12 feet away from point B in this direction, and in this direction. Then we have AE, which is right here, and it's 12 feet away, right here, because we already did the math over here. So an AE is going, if you look at it, because B's up here and AE is going this way, it curves this way, which is a counterclockwise curve. So then you plug it in and you solve for AE, which is a positive number. So the assumption that it's acting in tension is correct. The final step is to do the sum of the moment about point A. So if we go back over to look at point A, we can see that things acting about A are the P1 force, BC, and BE. So this is the important time for BE and where this number comes in. So when you're doing the distances, we know that P1 is 12 feet away from the perpendicular from where it's acting. So it's acting this way, so we're measuring this distance, right? So it's 12 feet from point A. Then we've got BC, which also starts 12 feet away because BC is going this way. And the perpendicular distance is this distance. If it's acting like this, then this is perpendicular. So this distance is 12 from A, like right here. Then BE, and the BE distance, the distance that this point is from here, because it's acting at an angle, is this measurement right here. So that's why it's important if you were given this side and this side, that's why you have to find the hypotenuse. In this case, you're given the hypotenuse, but in the future, you might not be. So you just do Pythagorean theorem to find it, but this is the distance that this force is acting because it's acting at a 45-degree angle. The other thing to note is that if it's your A is here, B is acting this way. If you can see that that's a clockwise motion, so that's also a negative. So then we just solve for the sum of the moment at A, plug in our P1, and we already know BC from over here, so we plug that in as well. The most important thing to note is that when you're carrying answers over, when we solve for BC, it was a negative. That means you need to plug the negative in here. Now, if you decide that you're going to look at this a different way and that clockwise is positive and counterclockwise is negative, that's okay as long as you stick to whatever you choose. I've stuck to this method because it's the way we've been doing things before, but if you switch it up, you just have to make sure that you stick to that method. So anyways, when we continue to solve this out, we get the answer for BE, and it's positive, so we can confirm that it's acting in tension. So I'll just zoom out so you can look at everything right here. Again, this is the problem from lecture 09, I believe, and you can use the same steps to solve the last problem on homework 5.